Zero clicks are the creme de la creme of remote exploitation for phones, well, for just about anything. And yeah, AI has certainly expanded the attack surface here. Especially now, we've sort of entered a new age of AI that has substantially accelerated the desire for new features.
That was Seth Jenkins from Google's Project Zero, and he's joining me today to pull back the curtain on a fascinating Pixel 9 exploitation chain. Welcome to Behind the Binary. Today we're diving into a zero-click attack that starts with a simple integer overflow in a Dolby audio decoder and ends with a full escape from the SELinux sandbox. We'll discuss how AI is driving these new features and how it's changing the attack surface of our devices. We'll also find out what it really takes to find bugs in the modern age of machine learning. Let's get started. All right, welcome to the podcast, Seth. Today we are talking about Pixel 9 exploitation chain. We're going to start our discussion by focusing on what I find to be really interesting changing of the attack surface and actually how this has been influenced by AI. And then there's two different bugs that we're going to be able to discuss in regards to a zero-click attack. One bug targeting the user mode, I suppose the user mode application or a decoder that is part of this AI attack surface that we're going to talk about, which then leads to a vulnerable kernel driver, a KSLR bypass, and the escape from the SELinux sandbox. I have that more or less correct.
Yeah, that sounds pretty close. Yeah.
Okay.
Yeah.
Okay. So you're here though to fill in all of the details. So welcome, Seth. Thanks for joining me today.
Yeah, thanks for having me. I'm super excited to be on here, and yeah, let's talk about exploits.
All right. So I think the best place to start is just this idea of zero click is not new, but the attack surface seems to be changing a little bit due to AI. And that's not meant to be a clickbaity statement. What can you maybe shed some light on, like, what is zero click and what do we mean by seeing AI influence the attack surface of our Android device? Because we're talking Androids, our Android devices.
Yeah. So, I mean, by zero click, we basically mean bugs where it would be possible to compromise a phone remotely without the user of the phone or the main sort of victim or whatever you would like to call it interacting with the phone at all, right? So we could call it like zero click, one click, in click based on how many clicks a user would need to do on the other end. So, for example, if you send someone a browser link, like a link to a web page or whatever, and they have to click that in order to exploit their phone, that would be considered like a one click, for example. One clicks are pretty common. We see a lot of bugs in the wild for Chrome and stuff like that. Those are generally one click bugs. But zero click bugs are a next step up where, like, the user on the other end has actually no idea that anything is happening at all. No amount of sort of like cyber hygiene can necessarily protect against a zero click, other than just keeping the phone off or, maybe blocking, any number that's not in your contacts, maybe. So, zero clicks are sort of, those are the creme de la creme of remote exploitation for phones, well, for just about anything. And yeah, AI has certainly expanded the attack surface here. I think one thing that has always been sort of the push and pull of the field of, making an interesting device and product for a user and also securing it is that you have these pushes for more features, more things, to compete with, all of the other people on the market who are also bringing their own new cool features and stuff. And you have, like, alongside of that, the security teams oftentimes acting as a little bit of a brake on that to say, whoa, like, as you implement these new features, you're adding new attack surface, you're adding new things that could go wrong on the system. And so you've always had this a bit of a push and pull in the field of, product development and how security interacts with product. And especially now, we've sort of entered a new age of AI that has substantially accelerated the desire for new features. It's unlocked a whole set of new ideas from people about, like, oh, I could do this new cool thing with this phone or whatever, with LLMs or with, machine learning neural networks or whatever. And those are cool and those are great ideas. And that's sort of innovation that, as a society, we love to see. I mean, that's kind of, what a lot of the technical sort of companies sort of thrive off of, and I think that's a good thing. But with that additional sort of pressure on features comes an additional pressure on security to say, are we implementing those features in a good way, in a responsible way? Are we rushing it before it's been like fully sort of tested to see if it's ready in terms from a security perspective? And so that push and pull is feeling that tension is very strong right now in the market. Where we have this sort of blend of AI sort of popping up like crazy, while we also exist in a world where vulnerability, remote code execution, and those sorts of vulnerabilities like zero clicks are serious concerns. And so balancing those two things is it's especially difficult for companies to manage right now. It's not like, oh, one of them is definitely right or one of them is definitely wrong. It's just a very difficult thing to balance for companies, and I think a lot of people are running into that.
So the first bug that we'll talk about here in just a little bit is directly a result of this expansion of kind of the feature set. Do you think at the same time, with LLMs writing more and more code, what role do you see them playing in writing vulnerable code, and also maybe on the converse, on the opposite side, helping to secure that code?
Yeah, like I certainly do think we have some data like how good LLMs are writing code. I think that there's sort of a very pessimistic view, which is that, oh no, it's a whole bunch of code that no one's ever looked at before, and then people are going to be shipping these features that are full of AI hallucinations. And that might be true to some extent. I personally am a little bit more optimistic than that, in the sense that I think that it's not my impression that like AI code quality is substantially or is destined to always be substantially lower than human code quality. And I think that there are cases where it could be higher. Humans are really, really great and really creative about writing bugs into their code. And we tend to be sort of inherently, oftentimes we can be a little bit of a lazy creature, myself included.
Yeah.
And oftentimes when it comes to sort of writing the code, like when I go to like now, if I go to like vibe code a project or something, sometimes I feel like the AI is doing a better job of writing the actual code than I am. Now, maybe I still play a very significant role in terms of like the design and sort of the vision for the project. But in terms of actual implementation, simple stuff like just checking error codes, right? And stuff like that. AI has no problem, has no trouble sort of spitting out stuff like that, and being somewhat thorough in that. And I think that that's something that could yield an advantage long term. I do think that there's a cost right now where, I think it can lead it can additionally influence that sort of like that feature push, right? Because it makes it much easier to ship a feature. It's still important that, code generated by AI is thoroughly code reviewed. I've certainly had AI make plenty of mistakes before, sometimes quite subtle. But I'll note that it's not like AI are making like whole new kinds of errors that humans would never make. Like maybe some of that is a little bit true, but I think this is sort of things where like, just as humans create bugs, AI create bugs too. And I'm not necessarily sure that I can vote as one as more reliable than the other. As it comes to finding bugs, AI are certainly revolutionizing that space as well. We're seeing, a new influx of AI discovered bugs, with programs inside of and outside of Google that are doing those sorts of things. LLMs turn out to be remarkably good at that sort of reasoning and stuff like that. And so, yeah, that's going to have a big impact on the vulnerability research field. It's in my opinion, at least. It remains to be seen exactly what that impact is. I don't think all the cards have landed on that yet. But it's new and it's exciting. It's an exciting time to be in the sort of like confluence of LLMs and vulnerability research. I think we finally sort of reached a point with machine learning and neural networks where they're really meaningfully contributing to the field. So yeah, exciting times. And we'll see how they play when it comes to like patch writing as well. I think that's another area where AI could be really useful in. I've seen circumstances where people patch bugs wrong all the time, But so far, it's at least I've had a mildly positive impression, honestly, of the ability of AI to patch bugs. I'm hopeful that that can sort of help deal with the influx of bug reports in the future. It's funny, I'll note this is all very subjective. I imagine that there are going to be people out there, who are rightfully and justifiably, much more pessimistic about the future of how AI is going to impact security and that it's all burning down. And perhaps I have a more optimistic view than average. But I do feel at least mildly optimistic that it's going to be net positive for
Sure.
security of devices long term. Even though short term, I think that we're biting off some substantial risk right now.
I am curious, like in the same vein of LLMs and their ability to help with this discovery. Yeah, I have this impression. I'm not a vulnerability researcher, so I have this impression that when you're doing a lot of your reversing work, looking at drivers and kernel drivers and such, that the code you're disassembling it, you're decompiling it, but that those authors are not adding a lot of intentional obfuscation versus, let's say, a malicious author or a red teamer who is, or maybe a game, like a game studio or a game developer that's really trying hard to make their code difficult to RE. Is that true? And if so, I mean, how is that going to impact? Because that's one of the areas that I'm a little hung up on is, if my LLM is able to read, it needs to read code that I've passed it, decompiled pseudocode from IDA, but IDA can't correctly decompile the code, then what is the LLM going to do with it? It's not going to correct it, is it? It's going to try to interpret it in a way that's likely going to be inaccurate and hallucinate and taint all of your work from that until you go back and correct it.
Yeah, well, at least when it comes to Android, we're pretty lucky for a lot of the sort of drivers and stuff like that we have nowadays. Most of it is open source,
Sure. Okay.
which is a big benefit. You can go and download the kernel source for your Pixel phone or from Samsung or any phone you want. You can go and find those drivers. Usually, there are exceptions. Sometimes developers sort of ship drivers sort of sneakily without publishing the source code for those drivers. Generally, obfuscation isn't too terribly a concern. Isn't too terrible a concern because we have the source. But there are cases where, like, for example, if you're looking at the actual firmware for one of the chips on like a phone chipset or something, you will deal with things that are difficult to reverse. Those are things that are oftentimes not open source and can be quite difficult to divine how they work. For example, with like Qualcomm, a lot of their chips use hexagon, which until very recently, I think when Bin just shipped some hexagon support, there's been no like major reverse engineering tool that supported hexagon. And that has an impact, right, on how easy it is to reverse and stuff like that. But yeah, it's a fair question about like how LLMs are going to impact the reverse engineering field as well. I think it could really help. LLMs seem to be quite good at sort of translating information, and so I'm optimistic that they'll be useful. But it's true, when it comes to obfuscation, that's how code could be made to be adversarial against sort of LLM reverse engineering, I think is a really, really fair and interesting question, maybe an unexplored question to some extent.
To set the stage here as we start to maybe transition to talking about the first bug, do you have any general approach that you follow for discovering bugs, for going after? I know a lot of your research is on Android. So do you have a methodology that, like, what is the trigger for you to decide to go look at a particular application or a particular driver, or to start a research process? Is it just something that you have to culminate over years of understanding the kernel? You just sort of know where to look, or does some bug report come in? I know you've done some work where you've had, like kernel log crashes where panics, but you've been able to use as a triage source. Where does it all begin?
Yeah, that's a great question. I think the answer is it varies. I think to some extent it is just a bit of like being able to just sniff out that something is going to be interesting. oftentimes it's going to be just based on sort of like what piques my interest. And to some extent, that might be as deep as it goes at the conscious level. But there are things that I look for in terms of finding something that's going to be interesting. Oftentimes I'm looking for something that's relatively obscure. I think obscurity is great because obscurity through security is not great. So finding bugs and those sorts of things becomes very plausible. When someone writes code and doesn't realize its impact, I think that's one of the cases that can have the biggest sort of change. Where someone develops some sort of library or some sort of driver, whatever, and doesn't think through, this is going to be accessible to a remote attacker somehow. I think it's realms like that that are super sort of like have a lot of potential for bugs, right? And drivers sort of sit in that space. When it comes to like mainline Linux kernel, for example, that's picked over quite thoroughly because there's a whole team of really excellent programmers and developers and security researchers who look at mainline Linux kernel, and they can find a lot of the bugs, and people spend a lot of time finding very complex bugs in there. When you switch to third-party drivers, these are often written by teams, working at companies who aren't developing a product and are just releasing these drivers back downstream to get incorporated into some sort of Android phone. And it adds additional sorts of layers to like being able to reason about like what exactly is the consequences of this driver. How carefully do we need to review this to see how potentially vulnerable it is to a malicious attacker who can access it and manipulate it directly. Yeah, so I think Android drivers sort of fit in a good space for security research there. And we've seen that sort of publicly. And so what my first thought here is like, what are the things that no one else is looking at when it comes to these drivers? I think this is one of the reasons why actually after 3 years of working on Android drivers, I don't think I've ever published a bug from Project Zero on a GPU driver. Everyone knows about GPU drivers. That ship has sailed, and to me at least, that ship has sailed. In the sense of like, I could go find bugs on a GPU driver. I'm sure, with enough time and energy and spending some effort, I'm sure there's plenty more bugs to find in there. But I've been chasing, the things what are the things that no one else is looking at? What are the things that no one else knows? If we burn all the bugs in GPU drivers, what comes next after that? And I find oftentimes those sorts of drivers are much less picked over than the GPU drivers, and maybe fewer bugs like ultimately, but still very fertile ground for plenty of bugs popping out. So
well, speaking of fertile ground, then we have a chain of bugs that you and colleagues were able to put together. That is the zero click. I guess how don't you tell us about what is it's audio coders and decoders, and where does this bug fit?
Yeah, I think this goes back to sort of our conversation about like how AI has influenced the security research space and the sort of the feature set space. So, in fairly recent times, Android started shipping this feature for audio transcription, so that like incoming audio messages are automatically transcribed into text using LLMs, using AI, right? And that in and of itself, that sort of adds a feature, right? Now, any sort of message arriving on a device gets parsed by an audio decoder, right? That's sort of the new feature, and that's the new attack surface, right? And when that feature got added, it was not limited to simply, okay, we're going to make sure that like, there could have been steps taken to reduce attack surface. So, they could have thought through, well, we're only sending audio messages of this one specific codec, MP3. I'm making one up. I don't know if it's actually MP3. I kind of don't think it is, in fact. But let's just say MP3 for the purpose of the conversation. And so we're going to make sure that only MP3 video or MP3 audio messages will be decoded, on the other end. But that's not how it got written. Instead, what got written was we receive an audio file of nearly any type, and we decode it just using the media decoding libraries. And that opens up like a whole bunch of additional attack surface beyond that what was necessary, right? It's not like, oh, we only have to worry about MP3 or whatever it actually is. Now we're opening up all of this attack surface for all of these different audio codecs. And one of the audio codecs that became an attack surface was Dolby's Dolby decoder, as I recall, EAC3. And so when we went and looked at this attack surface, we ended up having like a hackathon for the team. And we all went and hung out in a room together and just looked at this audio decoder for, a week. And sure enough, there was one very good bug from that set that was like an integer overflow because they didn't properly check to make sure that two ads didn't wrap around. And that led to a miscalculated length and ultimately a heap buffer overflow and overread in the Dolby sort of like heap in the Dolby media codec process. So yeah, very sort of great primitive, just from an attack surface that in another world would never have been presented to an attacker at all, and could have been avoided to some extent as well.
Yeah, because if I, again, correct my interpretation if at any point I deviate from the truth, but it's a user space library, so we're in user space yet on the device, and it's because the audio is defining in these internal structures. It's defining how much data it's sending and the size of the data, and so when the application library checks that, it doesn't verify that the length matches the actual length of the data. And then you modify the size to wrap, it allocates a small buffer and then overwrites with a much larger chunk of data. And then it goes beyond that, because just because you have an overwrite doesn't mean that you necessarily have control. So am I correct so far?
Yeah, that's more or less correct. I'll say that, like, as far my understanding, and again, this is an area where if you really want to understand how the bug works, you should go to our bug tracker and go stare. You can just go look up Dolby in our bug tracker, and you'll see all of the details from the people who worked very hard on finding and developing that POC. But my understanding is it's a specific type of metadata and a specific type of frame has a size attached to it, and that size gets added to, and that ad gets checked. And then there's a second add to it that's just like a page alignment or whatever. And that is the thing that I think led to additional trouble. But I could be making that up. I could be hallucinating. Humans hallucinate too. Don't let anyone tell you otherwise. And you can go and look at our bug tracker and grab the files and play around and make your own POC.
Yeah, absolutely. And there's some great blogs as well on the Project Zero blog website as well. So okay, so we have the overflow and then the ability to to precisely write. I think that's ultimately then the next stage of this thing is that with the overflow, you're able to overwrite I would assume a function pointer that allows for your arbitrary code execution.
Yeah, ultimately we do get a function pointer overwrite, and that's like sort of that's a great primitive to start off from. This one, it was rendered a little bit more complicated by the fact that ASLR is userland ASLR made it very difficult to figure out, like, okay, if I overwrite a function pointer, where am I going to make this thing jump to? That becomes very difficult to figure out. It's funny how, like, KASLR, we'll talk about spoiler, but KASLR is very easily bypassed, but userland ASLR turned out to be a really big headache when it came to writing this exploit. And so, in fact, the actual exploit technique for this bug, at least, did not go the route of like totally overwriting a function pointer, because you can't control where that goes. But if you overwrite the bottom couple bytes of a function pointer, you can preserve most of the ASLR bytes, the ASLR bits in a function pointer, and control by only like overwriting the last 2 bytes. You avoid most of the sort of like dealing with ASLR because you don't have to brute force it. So we end up with like a relative jump from where the function was supposed to go to some other sort of location nearby. And that's close enough. That's good enough to like find some good gadgets in there that you can utilize to get more deeper
Oh,
access
okay.
and build stronger primitives from
Okay.
that point.
Are you, because you're heap, so you're non-executable memory, so you're doing like ROP kind of stuff at this point still? Okay.
Yes, it's like ROP, JOP, COP, yeah,
All
all
that
of
good
that,
stuff.
all of those fun ops, yeah.
It sounds like a party and all the ops are invited. Uh, yeah, okay.
Yeah.
But eventually you get to the point where so you're building up your primitives. By that, you're getting maybe more reliable regions of executable memory that you allocate and can copy a more standard payload, some shellcode or something, I assume, or soften the environment to some point. But regardless, you're to
Yeah,
a point where you're able to execute what you want in the user mode.
yeah. Yeah, exactly. And there's some cool sort of like story about how exactly you get code execution in terms of like firing shellcode. There's always the possibility if you're really determined that you could just write an exploit in ROP. And originally we were talking about doing that. We're like, okay, I'm going to be shipping my side of the exploit in ROP. But thankfully that did not happen. That would have been fun. That sounds like a fun sort of like programming challenge for sure. But no, thankfully that did not happen. What we came up with an exploit strategy for getting shellcode that utilized a specific part of the Linux kernel sort of attack called proc_self_mem. And by opening this file and writing to it, we can overwrite executable memory in the sort of Dolby userland process. And that allows us to inject shellcode directly into the Dolby process just by opening and writing a file. And from there, we can just perform a jump to that location, and then we can get code execution and shellcode execution that way, without having to figure out how to like map memory as readable, writable, and executable, which turns out to be quite difficult because of SELinux.
Yeah. Okay. So I guess so. You get to the end of this chain, you have executable shellcode, but you have things like SELinux, and I'm not well versed in the Linux security ecosphere. So can you maybe give us the TLDR on what role SELinux plays here? I know it's the foundation for the basic, what I perceive as like a sandbox environment, and also are you at root level at this point? I would assume you're running under the privileges of the application, but I'm not entirely sure, I guess, how all the privileges work out. So like what are where
Yeah.
are you at, and what are the remaining hurdles? Because I think this sets the stage for bug number two.
Yeah, certainly. So once you exploit this bug, you land in a process, the Dolby media codec process in particular. It's assuming that you have code execution in there. You now are running as the media codec user, the media codec group, and the media codec SELinux context. SELinux is sort of one of the primary Android permissions managers on Android, and actually you can get it on like other Linux distributions as well. I think Red Hat uses it, for example. But it allows you to have much more granular control over what objects and what things a process can do. You can say you can't write to any files in this directory. It's a blacklist it's a whitelist, so it's off by normally you're not allowed to do something by default. But then if you add an allow rule in there, that's how you allow whatever you need. And basically that means that sort of anything that your process isn't normally doing is denied by default. All right. And so that's sort of a good well thought design. Instead of denying individual things, which takes a lot of effort. Instead, you deny everything and you only allow individual things, right? And so that really helps you sort of limit the attack surface. Basically, all processes in Android, even the highest privilege usually processes in Android, have an SELinux context that prohibits them from just doing whatever you want. And so oftentimes for an attacker, you need to find some other way to sort of neuter SELinux by getting into the kernel or something like that. So yeah, SELinux manages you quite a bit. Seccomp is also relevant as well. Seccomp is something that, like for example, Chrome uses for its sandbox, for its renderer, and that's quite useful as well. That lets you sort of like restrict individual system calls and stuff like that in a way that even SELinux doesn't give you that amount of control. And so this media codec context is supposed to be its own sandbox. It's supposed to be limiting how much access you have to the variety of different drivers and or attack surfaces and or other sorts of binder services, including having even a seccomp sandbox to say you can't even run most system calls. But unfortunately, that those did not prevent exploitation here. Actually, the seccomp at least was not enabled at all on the Dolby process, and so that ended up not being an issue. And then there were drivers that were in the sort of media that were accessible from the media codec context, media decoding drivers, which makes sense, but they were accessible from the media codec context, and those that represents really nice attack surface.
The seccomp then, is that an opt-in thing for application driver level, or was that, why wasn't that enforced on the media codec that we're talking about?
Yeah, so it is enabled on most of the media codec context. Media codec was supposed to be a sandbox. That's when it was originally sort of designed. The idea was that it was a sandbox because someone had the thought of, hey, there's going to be like a remotely reachable attack surface in here. We should probably like put this in a place so that it's like safer, and less able to compromise the rest of the system if someone finds a way in. And so someone had the prescience for that. But unfortunately, just with a certain set of media codec processes, including the Dolby process, the sandbox was not applied. I think, more of a case of just like an accident rather than an explicit decision. I think there's hope that at some point we'll resolve that issue. But at the point of at least exploitation, the seccomp sandbox was turned off for these devices for this specific process.
We get to the end of this bug, remote code execution. To take it back a step further, we are here because of a feature, audio transcribing of voice messages that are audio messages that are received on a device. So this is the zero-click nature of it. It's being transcribed by some, we're just saying AI because I'm not entirely sure exactly what is doing it. But features that are being added and enabled because of just this new capability that we have. You're restricted though, and so you want to now look for, and this is, I know, very common in vulnerability research, is to use and for, of course, those that are utilizing these for utilizing exploits for nefarious purposes, is that to chain. I mean, by nature, they have to oftentimes chain bugs together, because this bug enough wouldn't be enough for an adversary to utilize it. And I guess before we move on to the next bug, I guess, like, what would be at this point, what is a typical adversary looking for? I mean, they want to steal information off the device. They want to install spyware kind of stuff to intercept and log messages. Like what do you see normally at this stage? What is an attacker looking for to have access to on this device?
Yeah, so that's a question that I think that the GTIG, for example, is really well versed with. They'd be able to give you a much more thorough answer than I can. So as far as I can tell, the answer is that it varies from actor to actor. So different threat actors want different things. But it is true that generally at this point, an attacker, if they were to break in the media codec sandbox, they want control of the device more thoroughly. They want to be able to access all the data on the device. Maybe they want to be able to install some sort of malware and some sort of process running as root. So ultimately, what they're usually after, and I'm going to use usually in a very sort of like blithe way there, but I'm going to say usually, is they want to get root or kernel access on the device. They want UID 0 with all SELinux sort of neutered in some sort of way and prevented from impacting their ability to do whatever they want on the device. This bug does not get them that. In fact, just about any userland bug does not get you that. just in general. You do get some really nice occasional dirty cow style bugs where you can overwrite libraries that you shouldn't be able to overwrite and theoretically pivot into just about any userland process you'd like. Those bugs do happen. But even then, usually attackers want something more. They want full root SELinux off, and that nowadays generally requires kernel arbitrary read write or kernel code execution. And so oftentimes attackers are going to look at how do I gain access to the kernel? How do I exploit the kernel and get that sort of control?
So that brings us to bug 2. So the previous CVE 2025 54957, just for anyone that wants to know exactly what we were talking about. The next bug, CVE 2025 36934, is where you come in and you get kernel exploitation, privilege escalation, KSLR bypass. So how did the handoff go in the research to decide we have this userland bug, we need to see if we can chain it together with kernel level exploit?
It's funny because I think the handoff started happening before we even had the userland bug. I had this sort of idea of drivers are bad for many years. And I also had this idea of we focus on untrusted app. When it comes to finding bugs, we will oftentimes spend a lot of time working on untrusted app. What drivers are accessible from untrusted app? What can we do from untrusted app? Untrusted app, untrusted app. The reality is that there's more interesting contexts on Android other than this. And I had a sneaking suspicion that those were not as thoroughly audited, a little bit more obscure. That turned out to be a correct suspicion. And so actually when we started going into the Dolby hackathon, that very same week that we started looking at the Dolby hackathon and finding the bug, we ended up finding the bug in the Dolby decoder. I thought, hey, if we were to find a bug in that attack surface, what process do we pop out into? And what drivers can that process access? And so that sort of started the sort of route of looking into specifically on the Pixel 9, what drivers can I see from the media codec context? Because I had never actually done that prior to that point. And so this driver popped up, Big Wave, that does media codec decoding or whatever, and hardware. And so that immediately piqued my interest. So it all happened in the same week. I started looking at this driver. The team started looking at the Dolby decoder, and then 1 week later, we had the bugs we needed for a full RCE exploit. So
yes, okay, and that seems like a natural transition point to to see what drivers are available, to see how they're being communicated with, to make the pivot from the user space to the kernel. It sounds like you didn't find just one bug, though. You found multiple bugs, but there was one bug that was the one that allowed for this execution chain to continue.
Yeah. I found 3 different bugs in the Dolby. In the Big Wave device. One of those was a use after free read. You could leak 4 bytes from the kernel that way. One of them was a really weird bug. It was you got an object removed, or was it? You got it added to a linked list twice. You got this object that got added onto a linked list twice, which is not how linked lists are supposed to work. That violates one of the invariants of linked lists. So you got this really interesting sort of behavior or primitive or whatever. And I tried to chase that bug down quite a bit to see how to exploit that one. Because I thought, man, this would be a super interesting kind of exploit strategy, because we haven't seen but we get bugs like this, for example, when it comes to Linux kernel, we get double freeze, and double freeze are in general an example of this kind of bug, right? Where you have an object that gets freed twice, and when it gets freed twice, it gets put on a linked list twice. And so those bugs are exploitable because of just how that linked list is used. But we don't really see double linked list adds getting used outside of double free bugs. So I was curious to see if I could exploit this one. That turned out to be more difficult than I expected. But this last bug ended up being quite good because it was just a classic use after free, where the thing really was used in a pretty meaningful way to gain code to to like it was performing some sort of work that actually ended up like reading from the use after freed memory and then writing to kernel memory based on what was in that use after freed memory, and that's just a great primitive to work from. I basically, with like a heap spray, I got basically a really nice arbitrary write gadget, an arbitrary write primitive from there. By just like if I once the memory gets freed, I just allocate a new sort of object on top of that that's attacker controlled, and from that point, I just had a nice arbitrary
Okay.
write primitive. So
Yes, I don't. So it was a race condition, right? It would start a timer when
yeah,
the data would come in. The octal would be, I don't know how to phrase that correctly, but anyways, the request from user land, the
yeah.
kernel would come in, it would start a timer. If you, but it was like two things were happening to the memory. So if you immediately freed it and then overwrote, then the timer, when it eventually expire, then it would utilize that memory, and that led to the write.
Yeah.
Okay.
Yeah, so it's basically like that you issue an ioctl, and then so that has like this sort of, you do that through a file descriptor, and that file descriptor is associated with a specific object, and that ioctl ends up placing uh, an object associated with the file descriptor onto a separate linked list on that eventually gets picked up, or onto a separate array that eventually gets picked up by a kernel thread. But nothing really was protecting the case where if that kernel thread picks up the object and is starting to use it, and at the same time the file is closed, and that object could get destroyed simultaneously. So you get this race between a userland process and a kernel thread, basically, where the userland process can cause this kernel object to be destroyed while the kernel thread is still operating on that kernel object. And really nicely, you end up having like most race conditions can be quite tricky to trigger based on the race window and stuff like that. It could be pretty tough to sort of like fit into the race window, especially if the race window is quite narrow. In this case, the race window was enormous, like 1 second, just because you could get the kernel thread to basically just go to sleep for a second during the race window. And so you could it was basically deterministic, for all intents and purposes. I could get the kernel to sort of enter that 1 second wait and then free the object in that sort of space. And so yeah, it is a race condition, although it's so easy to trigger that it might as well not be. You just had to wait 16 seconds. That was the most difficult. That was the most annoying thing about the bug, is that you have to wait 16 seconds for each throw, just because that's how long it takes before you're able to free the object. But that's not a major concern for an exploit.
What role does KSLR play now? Like, because you want to get execution of code. I mean, if your ultimate goal is to get root, what are the next steps? How do you go about looking to disable SELinux, to change your account privileges? I mean, if you're running in the kernel, of course, and you can reliably, I suppose, send the code that you want to execute, well, then you're running as the kernel. But what's left at this point, and what role does KSLR play?
Yeah, so at the point that like we've performed some sort of heap spray, and now we have the ability to do an arbitrary write anywhere in the Linux kernel virtual memory. That's like a great primitive, but it becomes a lot more difficult or at least I was under the impression that it got a lot more difficult because I did not know any kernel address to write to. There are actually, this is some research that I've done previously. There was a previous sort of bug a couple of years ago. In fact, my very first project here, a blog post, was a case where on x86 Linux kernel, there were these objects that were placed at the same kernel virtual address every time. I think the thing that probably I found most difficult to figure out is like to get some sort of leak. When it comes to Linux kernel, breaking KSLR was one of the most painful parts. Just because you have to get that leak in order to be able to do anything else really super meaningful. And so to the extent I've managed to avoid that at least more than once, at least in that older case, there was a case where there was something on x86 that was always mapped at the same address, stacks that were mapped at the same address, and we were able to use that to gain to gain, basically stack buffer overflow and ROP chain with you were able to leak using that information. But I wasn't aware of something like that on ARM. But I had this niggling idea to like go and do my best to understand more about like how the Linux I had this idea that like the Linux kernel has this map of all of physical memory and virtual memory. And I wanted to understand more about how that worked because I had just like I just call it maybe the sixth sense. I'm not quite sure, but I just had this idea of like something here feels like fishy to me, and I feel like there's something like meaningful to go chase, but I'm not quite sure what it is. So I just need to understand how this works. So then I just started badgering my coworker with questions. Jan, my coworker, is just full of like knowledge about how the Linux kernel works. So I just started asking him questions, and I started going to do my own research about how this thing works and like what it does. And along the way, there was sort of this idea of like figuring out like how there's this sort of calculation for determining at what virtual address any particular physical address is placed at. And so just maybe I said this already, but just the idea is that like there's a whole linear mapping of physical memory in the Linux kernel virtual memory. It's just like one-to-one. The first physical page or the 0th physical page is at this address. The first physical page is at that address plus 0x1000. The 10th physical page is at that address plus 10 times 0x1000, on and on and on, right? It's just that, right? Every PFN is perfectly mapped next to every other PFN in virtual memory. And so it's just like, how does it determine where exactly to place that in virtual memory? And so when I started doing that research, I eventually tracked down where the kernel ASLR should be happening for that sort of object. There was this variable called memstart address that got like added onto the sort of calculation that was supposed to change the location in virtual memory where this thing got mapped. And so then I went and like looked at memstart address on a Pixel 9, and it was this value. I can't remember what exactly the value was. And I was like, okay. And then I rebooted the device and I checked the value again, and the value was the same. And I was like, whoa, what is up with that? I rebooted the device a couple more times, and indeed the value was always in the same place. And that sort of triggered the idea of like, what actually is going on here? And my discovery that indeed for the linear mapping, the kernel was always placed at the same location. And that means that with its arbitrary right, you could just target anything in a linear map. Anything in physical memory became a target. Now, some of the linear map is not marked read write, so some things could not be targeted. But like kernel.data and stuff like that was marked as read write, and so that became a target for the next stage of the exploit.
And that's interesting because that is I saw that some of the patches or like issues that have been opened up around this is a sort of a fundamental issue with how this memory mapping is occurring. It's I guess I don't know all the complexities of what it would take to fix this, but some of the responses that I saw from some of your requests were, working as intended will not fix. Is that kind of the state of where this ability to, because ultimately this allowed you to, persistently write to enough of the kernel memory to bypass SELinux?
Yeah, and to get full like kernel arbitrary read write in particular. Okay. So yeah, it's true that everything was technically working as intended. And I think this is a really interesting sort of circumstance where at least my knowledge as a security researcher lagged behind sort of what was like vaguely public knowledge. I'm not even going to call it an open secret. It's just like technically it's just like an open thing that like, oh, hey, the linear map is not randomized on ARM64. And in fact, there are just like public patches that you can just go and see where it's like, yeah, we're just removing the randomization. And the decisions for that were a couple. But suffice to say that was technically public knowledge. It was just public knowledge I just wasn't privy to. And I think maybe that many other security researchers might not be privy to, but at least I wasn't privy to it. But along with that came the cost of the Pixel bootloader always places the kernel at the same physical address. And that's also sort of its own sort of open secret in the sense that you can go and look at proc IOMIM and see that the kernel is always placed at the same physical address every time. Basically, the result of these two open, not secret things, with the kernel being placed at the same physical and therefore the same virtual address in the linear map every time, ultimately had serious security relevant consequences. These are just things that developers do, and they do it for good and meaningful reasons. But the consequences end up being quite significant for the kernel in this case, because it makes a whole set of arbitrary write vulnerabilities much more easy to exploit.
So the end of the chain, the end of the bug, the ability to influence things like SELinux, that's still there. It's still would you call it a vulnerability at this point? It's just how the system is designed, and you mentioned it, but just to reiterate, we're talking Android and ARM 64 as the underlying architecture.
Yeah. So once you have the ability to sort of arbitrarily write to kernel.data, your primitive is quite good. You can control, once you can control anything in .data, the getting kernel arbitrary read write. Ultimately, turning off SELinux is sort of like a secondary task in the process of really just what you want in order to do that, to turn off SELinux, is just get kernel arbitrary read write. Right. So at this point, I have a kernel arbitrary write, and I also have access to, I can also write to anywhere in kernel.data. And from there, it turns out to be pretty easy, to get kernel arbitrary read write. Once you have kernel arbitrary read write, turning off SELinux is slightly more difficult on Samsung phones, but at least on Pixel, it's just a single Boolean value in kernel memory. And so you can simply just, once you have our kernel arbitrary read write, it's flipping that from 1 to 0, and then you have SELinux in a permissive mode instead.
Okay. And there's the full chain. So one specially crafted audio file, and a whole bunch of pain later. You own the device.
Yeah.
But when you read the blogs, it seemed like there was maybe, I don't know, community consensus or discussion, at least in the community, that this wasn't, that these, I don't know, was it the first bug maybe that couldn't lead to full control of the device or something? Why did the team set out to prove this zero click scenario?
Let's see what was going on there. I mean, I think with almost any sort of bug, there can be some sort of skepticism about security impact. Sometimes the security impact is obvious, but downplaying of security impact is a common thing that we sort of just experience. People saying this bug isn't actually exploitable, it's not actually useful, and Dolby put something in their advisory when they made an advisory down to the other sorts of companies that use their tool. They were like, we think that this is only maybe possibly exploitable, but we don't think that this is exploitable. You can cause a crash. That's the only thing that matters. It's just a crash. But I think we already had the idea in mind of it's worth writing the exploit for something like this. I don't think up until this point our team had ever written a zero-click exploit chain for a mobile device. We'd reversed several for when it came to some of our in the wild sort of research that we've done in the past. But in terms of writing one on our own, that was a new sort of idea. That was a new sort of thing to go play with. And that certainly influenced it. Once it was we have enough bugs to get a zero-click exploit chain, I think it was a pretty easy decision to just go and chase that. Part of what our team does is, we try to write exploits in order to, call attention and find new interesting exploit strategies, to call attention to bugs, to say, these bugs are actually serious. And I think that's certainly played out here. I think, we discovered interesting things about sort of the Linux kernel along the way of writing this exploit, like the linear map and the weaknesses in kernel ASLR. We're able to demonstrate, yes, these bugs are absolutely exploitable. Zero-click exploits are alive and well on Android devices, that are, or basically, well, just on mobile devices in general. And yeah, it's possible to do this with just 2 bugs. And you mentioned that a lot of pain later, but I must say it's not as much pain as I think our team expected, or as much pain as we want. We want. I mean, I guess that's sort of role of Project Zero, right? Our goal is to make 0 day hard, and so we want to increase the level of pain. And I think here the pain was not as high as we were hoping it would be. And I think that's a relevant point there. But I mean, I guess that's why we do the research, right? Is now I think it's slightly more painful than it was the day before.
And absolutely, I think a big part of it too is it's not just getting the CVEs issued, and I imagine we could have a whole conversation on working with vendors and responsible disclosure and all that, but surfacing it to the public and just everybody who's involved in the whole cycle of developing applications and drivers and Android and pushing features. And I think it's good to understand and see that this does have a significant impact what you're putting on the device and the role you play. So it's great to see not just knowing what Project Zero does, but seeing those results and sharing those with the world, the community. So thank you for doing that.
Yeah, absolutely. I mean, I think that's one of the sort of founding sort of principles of our team is we want to be a team that's open. We don't want it to be siloed away. We want to be sharing our work with the greater community and calling attention to these sorts of things. We think that that's a really relevant, important aspect of security research, is being open about that security research, and demonstrating that even a company or organization as big as Google can be open about this sort of security research and can share and talk about the sorts of developments, and can also be sort of a little bit self-critical, right? To say, hey, we look at our stuff too, and we're open about that too. And I think that's sort of I think that stands as a bit of a mission statement for the team, to sort of demonstrate that that's possible. And that's not something that we as a whole security research community should be scared of, but it's something that we should embrace. Openness ultimately improves the safety for everyone, right? And I think that's a philosophy that our team really tries hard to live out in practice.
I couldn't agree more. I think that when I first looked at the associated blogs and saw that this was the research was done on Pixel devices, I thought, well, that's just a great sign, I think, of the role that Google plays in all of this, and just it could have been very easy to tell the team, hush, keep this under. We'll patch it quietly. We'll work with the vendors quietly. We'll kind of make this not get a lot of visibility, but doing the opposite of that. I think that is just a great strategy, and it's just great to see the priority that it takes, the focus that the security takes for the team and the work that's being done. Well, a fascinating process, fascinating story. I think a really interesting case of bugs, and what's really great about it is anybody that wants to go and really follow along with your work. We've made mention of the blogs, you've made mention of the POCs. It's all out there, it's all visible, it's all public, so feel free to hack away. Seth, thank you so much for your time today. Really enjoyed the conversation and look forward to doing this again soon, hopefully in the near future.
Yeah, thank you so much for having me.
And that's all for this episode of Behind the Binary. Thanks so much for tuning in. If you enjoyed the show, please consider subscribing and leaving a review. It really helps us to reach new listeners. Until then, stay curious and keep exploring.